What's up everybody and welcome back. This is the Control Engineering Geek. In this video, I am going to introduce a simple example on how to formulate an MPC problem. But before that, it is important to state that most of the materials introduced here are taken from Predictive Control with Constraints, a book written by J.M.A.C. Joski. A paper entitled as The Linear Control Strategy for Paper Making Process, which is written by Ying, Ming Rao and Xian Sun in 1992. And the user guide of the Model Predictive Control Toolbox. Our example is a paper-making machine with headbox. The paper-making machine at a paper mill produces the super-thin condenser paper. The following figure shows a diagram of the machine and its functionality can be described as follows. The stock from pulp workshop is pumped into a mixing box where it is mixed with the white water. The mixture goes through the filter where the dregs and stock is removed. Then it is filled into head box. The next step is to place the stock onto the forming wire and to remove most of the water to form paper. The paper sheet goes through the press part and dryer section or the cylinders to remove the remaining water, and finally the process of production is accomplished. It is well known that the headbox system is very important in paper-making process. The level H2 and consistency N2 of stock in the headbox are the main factors affecting production quality. In general, one can consider both flow rate of white water and stock going into the mixing box as the control variables U1 and U2 to control the level and consistency of stock in the headbox. This process of making paper can be represented in a schematic presentation as following. From control perspective, one can define the followings. As control manipulators, we have the stock flow rate GP as well as the white water flow rate GW. As states, we have feed tank level H1, headbox level H2, feed tank consistency N1, and headbox consistency N2. As measured output, we have H2, N1, and N2. And finally, as controlled outputs, we have H2 as well as N2. Now, as I've defined the control-related variables, we can drive the related differential governing equations. For the mixing tank, we could use the mass balance law. This gives the following relations. The involved new variables are, NP is the consistency of the stock from pulp workshop, NW is the consistency of the white water, G1 is the flow rate of the mixing stock out of mixing tank, and finally, A1 is the cross-sectional area of the mixing tank. For the headbox, the mass balance law gives the following differential relations, where A2 is the cross-sectional area of the headbox, whereas R2 is the flow resistance of the headbox. Combing both group of differential relations, we end up having for the mixing tank and for the headbox. As we can see, this is a bilinear differential equation. This means that in order to use linear MPC, we need to have a linear model. One can use the following defined steady-state values. Thus, using linearization technique, we can have the following linear, continuous set of first-order ordinary differential equations in this form of the state space. Here the time is given in minutes rather than seconds. Assuming a sampling time of 2 minutes, one can utilize the MATLAB function C to D to discretize the driven linear state space. The corresponding result is given as. Here, both measured and controlled output relations remain the same as with the continuous time state space. Now, let us assume that the prediction horizon HP is 10. This means that we are looking 20 minutes into the future. Also, let the control horizon is 3. For the cost function, let the weighting matrix at time I on the deviation is and let the weighting on the control change be given as. The values of the matrix Q is set as shown because the consistency is more important than the control of level. Thus, errors in consistency and 2 are penalized more than errors in level H2. In the matrix R, however, both control actions are penalized equally. These two weights are assumed to be true for all times I along the corresponding horizons HP and HU. Since there is no delay in the process, errors are penalized from the first step, namely HW is set to 1. The two valves on the stock as well as white water flow rates are scaled so that their range of operation is as shown. Their slew rate or maximum rate of change is set up such that the valves can move through 10% of their range in one step, which is 2 minutes. Thus, each valve change is saturated as shown. Finally, the headbox level H2 is constrained so that the headbox never runs dry or overfills as shown by the following constraint. According to what have been presented and assumed, we can set up each constraint type as following. For change in the control valve, as we have HU is equal to 3, we have the following constraints along this horizon. For the range of the control valve, we can say the following as well. Note that as HU is 3, and we have 2 control actions, thus each controller will have 3 future prediction in total of 6 total items and vectors of change in control and range of control actions. For the controlled output, as we have HP equal to 10, we have 10 future prediction as shown. We will say more about this constraint later. Now, let us go back to the constraint that limits the change in the valve changes. According to the given limits, we can say the following. Note that all control changes are saturated along the control horizon HU. We can rewrite this constraint in the form that we have learned in the previous video as. Thus, the E matrix is given as. Similarly, with the given limits on the control ranges, we can write the saturations in the control range along the control horizon as. Following the same procedure with the constraint and change in the control, we could have. Once again, the F matrix is given as. Lastly, for the control output constraint, we could write the following along the prediction horizon HP. Note that, as I explained in the previous video, the constraint on the control outputs should be on all involved or considered controlled outputs regardless of whether they are being constrained or not. Thus, the right vector of the control output should be as shown, which is of length of 20 by 1. This is because we have a prediction horizon of 10 and, at same time, we have 2 controlled outputs. Thus, each output will have 10 future prediction, and this will make our final vector to have a length of 20 by 1. Keep in your mind, we have taken HW to be 1. If we considered HW to start from 0, then each control output will have 11 future prediction, and this will make our final vector to have 22 items. Because of space limitation, I will only consider writing the constraint for the first predicted value of Z1 hat. Given that we have the constraint on Z1 hat at k plus 1 as. Then, by following the same steps we have done for last 2 control constraints, we can write. You have to have similar results for other future predicted values of Z1 hat from k plus 2 all the way down to k plus 10. Therefore, the G matrix will have a dimension of 40 by 21. I hope this presentation was helpful. Thanks again for watching the video, and please do not forget to hit the subscribe button and activate the ring button as well. See you soon.